Hey guys, let's start a single variable calculus. So, if you are in VIT, then this is probably the first subject that you have done in your first semester. So, let's just dive right into it. So, let's see what a derivative of a function is. At a point. So, for example, you have a function from A to B and it is real. Let's say there is a point C which lies between A and B. Then f is differentiable at C if your limit where x tends to C, fx minus fc divided by x minus c, or f dash c, which is limit h tends to 0, f of c plus h minus f of c divided by h exists. This is when your f will be differentiable at c. Now let's talk about your left hand and right hand derivative. So left hand derivative, you can write this as LHD. So again, for a function a to b, here a and b are included, which is a real function, and c lies between a and b. So if limit of x tends to c minus, that is something very smaller than c, fx minus fc divided by x minus c, or limit h tends to 0, f of c minus h minus f of c divided by minus h exists. Then you can say LHD exists at C. Small c. Similarly, your right hand derivative, or RHD, for a same function f from a to b, which is a real function where c belongs between a and b. So if your limit x tends to c plus, so something very slightly bigger than c, fx minus f of c divided by x minus c, or limit h tends to 0, f of c plus h minus f of c divided by h exists. Then RHD exists at C. Now the next thing we need to see is differentiability in some interval. For example, you have a function f that is going from a to b and it is a real function. So this f is said to be differentiable in a to b if f dash c exists for every c that is between a and b, which is basically a less than c less than b. So c lies between a and b. If you can differentiate the function at c and the point exists, that means your function is differentiable in that interval. So now let's look at a theorem. If a function is differentiable at a point, it is continuous at that point. So basically, differentiability implies continuity, but this is not necessary that continuity will imply differentiability. So let's look at the proof for this. This won't be asked in the exam, so you can skip it, but I'll just show you the proof. So let f be a function which is differentiable at x is equal to a. So I can write fx minus f of a as fx minus f of a divided by x minus a multiplied by x minus a. So now let's take limit on both sides. So limit of f of x minus f of a is limit of x tends to a, fx minus fa, here also it's x tends to a, divided by x minus a into limit x tends to a, x minus a. So what is this? This is your f dash a, and limit of x tends to a, x minus a is when you put x as a, so this will give you 0. So this becomes 0. So you get limit of x tends to a of fx as fa, which means this is continuous. So your differentiability implied continuity. Now let's look at a question. Check if fx has a derivative at x is equal to 0. So your function will be given to you like this. It might be in parts. So your function is given that when x is 0, the value of the function is 0, and when x is not 0, the value of the function is this. So what we need to do, we need to find both LHD and RHD. So let's start with the LHD. So f dash 0 is equal to limit h tends to 0 f of 0 minus h minus f of 0 divided by 0 minus h. So this becomes f of minus h minus 0 divided by minus h. So I can write this as minus f of minus h divided by h. Or let's write limit h tends to 0 everywhere. Okay, so what is it when h tends to 0 but is not exactly 0? It's given to us in the question. It's this. So let's replace this. So I'll just write it as limit h tends to 0 minus 1 by h, and let's write f of minus h as minus h square sine of minus 1 by h. So this becomes limit h tends to 0 minus 1 by h into h square sine 1 by h, and I'm going to take the minus outside. So you can write this as limit h tends to 0. You can cancel the minus and you can cancel 1h. So you get h sine of 1 by h. And if you put h in this, you're going to get 0. Now let's check for your RHD. So f dash 0 limit h tends to 0 becomes f of 0 plus h minus f of 0 divided by h. This is limit h tends to 0 f of h divided by h. So again you get limit h tends to 0 1 by h into h square sine of 1 by h. So you can cancel one h, and again when you put in the value of h as 0 you get 0. So as LHD and RHD are equal and they're both equal to 0, that means your derivative exists and it is 0. This is your answer. Now if you get some question where your LHD and RHD are not equal at the point, that means your derivative doesn't exist at that point. Now guys, let's revisit a theorem you probably did in 12th class. It's called Rolle's theorem. So this theorem says that if you have a function defined in a comma b, which is continuous in a comma b, differentiable in a comma b, and third, your f of a is equal to f of b, then there exists at least one c that lies between a and b such that f dash c is equal to 0. Or you can say the slope dy by dx at c x is equal to c is equal to 0. Remember guys, when you have square bracket it means a and b are included, and when you have the normal brackets it means a and b is not included in the range. So let's look at an example. Verify Rolle's theorem. Fx is given to you as ex sine x in 0 to pi. So since ex is a continuous function and sine x is also a continuous function, so their product ex sine x is also a continuous function. Now let's try to find f dash x. This becomes ex cos x plus ex sin x. So this can easily be differentiated in 0 to pi, which means this is differentiable in 0 to pi. Now let's find f of 0 and f of pi. So f of 0 is e raised to 0 sine 0, which is 0, and f of pi is e raised to pi sine pi, which is again 0. So these two are equal, which means your Rolle's theorem is verified. So I'm gonna stop here and we'll cover the Lagrange's mean value theorem in the next video. If you guys have any doubts, leave them in the comment section and I'll answer. Thank you.